Hello friends, good morning. Last time we have already discussed about our last topic of the chemistry, that is green chemistry and nanochemistry. Out of that, in my last lecture, I have already finished green chemistry. In today's session, we are going to revise briefly green chemistry within 5 minutes, and after that we will start our nanochemistry. So far as green chemistry is concerned, green chemistry is nothing but the environmental friendly chemistry, that is known as green chemistry. Green chemistry is based upon 12 principles. What are those 12 principles? These are those 12 principles. If you follow these 12 principles, then we follows green chemistry. Let us see one by one the 12 principles of green chemistry. Point number 1, prevention of waste or byproduct. It is obvious that if you want to prepare a chemical compound, then let us prepare that chemical compound, not the byproduct. What I mean is, as far as possible, try to reduce the quantum of byproduct. Whatever byproduct you are getting, let us try to make it zero. Let us try to eliminate it. It is known as zero waste technology. Means let us make the byproduct as a zero. If it is not possible to make the byproduct zero, let us reduce the byproduct. Means let us reduce the quantity of byproduct. And if you are not able to do these two things, or if we want to do it in another way, let us recycle the byproduct. What does it mean? This recycle is also done in most of the plastic industry. For example, plastics are non-biodegradable. They cannot degrade. Most of the plastic, I am saying, they cannot degrade with the help of nature. So what you do is create such a plastic which can be recycled. Means prepare plastic, use it, again throw it and let us recycle it and again use it. You can do like this. That is known as a recycle. Another thing is that, for example, whatever the byproduct of the reaction 1 is concerned, reaction A is concerned, the byproduct is used for the reactant of another reaction. For example, I tell you one thing. The bottom ash of thermal power plants, whatever ash we are getting after burning the coal, the ash, we cannot eliminate the ash. So what to do? Let us use that ash in a very innovative manner. Let us use that ash in brick industry. Means in brick industry, it is one of the reactant, one of the starting material. Means we have used the ash, right? In this way, we can handle this prevention of waste or byproduct, right? Next is atom economy. What does it mean by atom economy? Atom economy is nothing but whatever reactant you are, for example, you are converting reactant A into, we are getting, for example, B plus C. What I want is, I want to convert A into B, C is our byproduct. If C is our byproduct, then whatever substance we have used as A, most of the substance, it should get converted into B and not C, because C is our byproduct. As far as possible, reduce the quantity of byproduct and increase the quantity of this product, which is known as atom economy. After that, next is less hazardous chemical synthesis and this designing of safer chemicals. These 2 points are almost same. There are very many chemicals which are hazardous in nature, which are carcinogenic in nature, which are not human friendly, which are not environmental friendly. For example, benzene. In those industries where benzene is used as a raw material, at those industries, the workers, millions of workers are facing the problems of health. So what to do? Design the chemical reaction in such a way that we are going to avoid the use of benzene. We are going to design the reaction in such a way that we don't use benzene. Instead of benzene, let us use some another chemical material. Means we are using safer chemicals. We are using less hazardous chemical substance. Right? After that, safe solvents. There are two types of solvents. One is aqueous solvents and another is non-aqueous solvents. Means water is acting as a solvent and another non-aqueous means, for example, alcohol, chloroform, carbon tetrachloride, liquid ammonia, carbon disulfide. These are also acting as a solvent. What happens is, if you use water as a solvent, then water is cheap in nature. It is naturally available. You need not to prepare it. Instead of water, if you are using alcohol, then alcohol you need to prepare. It means while preparing alcohol, you are going to increase the pollution. Means as far as possible, try to conduct the reaction in such a solvent, for example water, that it will be user friendly, economic friendly and environmental friendly also. Means these safe solvents we need to use. After that, energy efficiency. As far as possible, try to conduct the chemical reaction at a room temperature and atmospheric pressure. Why? Because if you are conducting the reaction at a high temperature, means for heating that type of reaction you need energy. If you want to use energy, means you want to create some heat energy somewhere, means you are burning coal or whatever it is. So therefore avoid the reaction at high temperature. Try to conduct the reactions at low temperature. Another thing is that as far as possible, try to use the modern methods of heating techniques like microwave oven or like that. Right? After that, removable feedstocks. Means whatever chemical substances we are using, for example, we are using chemical substance coming from crude oil. Instead of using chemical substance coming from crude oil, let us use the substitute which is coming from plant material. Because if we are using the chemical substances coming from crude oil, we are going to increase the pollution. Instead of that, let us use the chemical substance which is obtained from the nature but from plant material. Right? That is nothing but removable feedstock. After that, reduce the derivative. What do you mean by reduce the derivative? For example, I am going to conduct a reaction like this. A is getting converted into B, B is getting converted into C, C into D. This D is our required product. What you want is, you want a D, you don't want a B and C. But we cannot do anything. The reaction runs in such a way like this. So what you do is, you design the chemical reaction in such a way that this A is getting converted into D directly. Reduce the derivatives. Whatever B and C is getting created, need not to do that. Design the chemical reaction in an alternative manner that A is getting converted into D directly. Right? This is nothing but reducing derivatives. After that, use of catalyst. What happens is, when you use the catalyst, the reaction is conducted in less time. If you are conducting the reaction, you are completing the reaction in less time, means you are, what should I say, means you are reducing the energy. If you use catalyst, for example, hydrogenation of vegetable oil, nickel, platinum, palladium is used as a catalyst. In that reaction, if the reaction is carried out in the presence of catalyst, then the reaction is completed in very short time period. If you complete the reaction in a very short time period, means you are going to save the energy. Therefore, as far as possible, try to use the catalyst. Next, design for degradation. Simple words, for example, plastics. Plastic cannot be degraded. Most of the plastics cannot be degraded. So, as far as possible, design the chemical reaction in such a way that you get such a chemical product which can undergo degradation with the help of nature, that is known as design for degradation. After that, real-time pollution prevention. For example, if you are starting the reaction at this point and ending the reaction at this point, and the time in between these two is very high. If the time is very high, and if you are carrying the pollution analysis at the end of the reaction, then it is of no use. Why? Because if you are carrying the pollution analysis at the end, the pollution has been taken place. Pollution has been completed. For example, reactions taking place in the nuclear reactors. What you do is, if you start the reaction at this point, if the reaction progresses, in between the points, you carry the pollution analysis and try to avoid it. Again go ahead, let the reaction progress, again do the pollution analysis. Again go ahead, let the reaction progress, again do the pollution analysis. So that real-time pollution analysis is going to reduce the pollution. It is going to reduce our pollution. After that, accidental prevention. What is that? In n number of industries we carry n number of reactions. By that, in most of the gaseous reactants, what happens is the reactions are explosive in nature. Sometimes some fire hazard takes place. Sometimes some accidents takes place. As far as possible, try to avoid these accidents. Right? These are those 12 points or 12 basic principles of Next, what we want to discuss is role of green chemistry in our day-to-day life. Role of green chemistry is very important in our day-to-day life. You imagine that if you follow these 12 principles, we are going to produce such a chemical compound which is pollution free. We are going to reduce the pollution. We are going to reduce the pollution means we are also helping the nature. We are also helping the ozone layer depletion problem and all those problems. Means we are reducing the pollution. Therefore, green chemistry plays an important role in our day-to-day life. Up to this moment, we have already finished our green chemistry. We have discussed its advantages and all those things. Now, let us discuss only about nanochemistry. This is our nanochemistry. What is nanochemistry? Nanochemistry is nothing but the combination of two sciences. That is nanotechnology and chemistry. You know chemistry. I need not explain you about that, and I will not explain it. So far as nanotechnology is concerned, this concept of nanotechnology was first of all proposed by Japanese scientist. The name of the scientist was Tanio Nariguchi. He was the Tokyo University professor, and this person introduced the concept of nanotechnology. Let us first of all understand the meaning of the nano. What do you mean by nano? This nano is nothing but dwarf. Dwarf means what? Small. How much small? That we are going to define it. In fact, nano is nothing but extremely small. Extremely small. Right? This is nothing but nano. The word nano has been derived from the Greek or the Latin language word which is known as dwarf. Meaning of it is small in size, small in dimension. That is known as nano. Now, let us define nano. Let us define 1 nanometer dimension, or how much is the 1 dimension, 1 nanometer length, how much is it? 1 nanometer is nothing but 1 billionth of 1 meter. Let us not confuse now. Let me explain you. 1 nanometer is nothing but 1 billionth of 1 meter. Now let me consider these 2 points. And let me assume that the distance between these 2 points is 1 meter. The distance between these two points is 1 meter. What is 1 nanometer? 1 billionth of 1 meter. 1 meter we need to divide into 1 billion portion. Means what? What you do is you divide this into 1 billion portion. 1 billion I am saying. In fact, it is not possible to plot 1 billion points at this scale. You just imagine that 1 meter length has been divided into 1 billion part, and out of that 1 billion part, let me remove one part. That one part is known as 1 nanometer. Means 1 nanometer is nothing but 10 raised to minus 9 meter. मैं अपनी भाषा में बताता हूँ. For example, you have 100 crores. Out of that 100 crore, let us remove 1 rupee aside. उस 100 करोड़ में से 1 रुपए को बाजू में रखते. That 1 rupee, that 1 quantum out of 100 crore, comparing it with 100 crore, that 1 rupee is known as 1 nanometer. You can compare like that, right? This is nothing but 1 nanometer, that is equals to 10 raised to minus 9 meters, right? So, for your understanding, now let us give you some examples in day-to-day life. Those examples you will came to know that how much is 1 nanometer. I will give you one scale. On that scale, I will give you some examples that which, for example, virus or a bacteria or a glucose molecule or tennis ball, how much is the dimension of that particular thing, so that you will came to conclusion the size of 1 nanometer. So as to explain you the length of 1 nanometer, let me compare 1 nanometer in day-to-day lives. Some examples. How much is 1 nanometer? Let us compare it with tennis ball. For example, tennis ball is having dimensions which is equal to almost I am saying, approximately I am saying 10,000 crore nanometer. After that, bacteria is 1000 crore nanometer in dimension. Virus is about 100 nanometers. Antibody of any disease is about 10 nanometers, and glucose molecule is about 1 nanometer. Now, whatever molecules we prepare as a bulk in the laboratory, they are having some definite physical properties. For example, consider any chemical substance, any compound, any material. For example, consider a sand. If the sand molecule, if the sand particle is extremely large, you can visualize it. It is having certain physical properties. Let me consider, instead of sand particle which is large, let me consider small size sand particle. This sand particle is also visual with the help of your eyes. You can visualize with the help of your eyes. You do not to use microscope or like that. Means this is also that much large, but this is very large. The physical property of this particular material and the physical property of this particular material is absolutely same. There is no difference. But if you reduce the size of any substance, if you reduce it to about 1 to 100 nanometer, means if the substance which is prepared is not prepared at bulk level, it is prepared in very minute quantity, and it is having its structure in such a way that any one of the dimension of that particular substance is in the range of 1 to 100 nanometers. For example, carbon. The normal carbon is having its own properties, whatever physical properties it is having. But instead of preparing normal carbon, let us prepare such a carbon which is having its molecular size or dimensions which is extremely small. It is at nanometer level. For example, 2 nanometer size of carbon nanotubes. If you reduce the size of or the dimensions of this particular chemical substance molecules, then the physical properties of those molecules is extremely different as compared to bulk substance. Means if we are going to control the size of this size of the substance at a nanometer level, if any one of the size is in between 1 to 100 nanometers, then the physical properties, what are those physical properties? Maybe optical property, thermal property, electrical property, magnetic property, catalytic property, all these properties I have written at this place. Means carbon at a bulk level, at a large quantity, is showing different property. But the same carbon, if its size is very minute and its dimensions are controlled in this range of 1 to 100 nanometers, dimensions are controlled at 1 to 100 nanometers, then its physical properties, that is, which physical properties? Some optical property or structural property or thermal property or catalytic or magnetic or electrical properties change to a very drastic level. Means bulk carbon is having different properties and this nanomaterialized carbon is having very different properties. In this chemistry, nanochemistry, we are going to study in details the chemical substances having size in between 1 to 100 nanometers.